Good morning, good afternoon, or good evening. We are going to review lesson 5.1, describing rotational motion. This is for the benefit of anybody who missed the lesson the first time it was presented in class, or who would just like to review. So let's start by talking about how we measure rotation. Just like with linear motion, rotation can be measured in several different ways. The SI unit for measuring rotation is a radian. If you remember from math class, a radian is the angle subtended when the radius is laid out along the circumference of the circle. Imagine taking a raw spaghetti noodle and using it as the radius of a circle. So if you were to place the noodle on the counter and just spin it around one end, the other end would trace out a perfect circle. Now imagine that you boil that spaghetti noodle and lay it out along the circumference or outer edge of that circle. The angle that boiled noodle would make is 1 radian. And a radian is roughly equal to 57.3 degrees, which degrees is another way of measuring angles or rotation. A degree is 1/360th of a circle. You can also measure rotation in terms of revolutions, where a revolution is one complete trip around a circular path. Down here in the corner of the screen, you see a conversion factor that will help you go from revolutions to radians to degrees and back again. 1 revolution is equal to 2 pi radians, and 2 pi radians are equal to 360 degrees. Now, just like with linear vectors, rotation is also designated by signs. We use positive to indicate anti-clockwise rotation and negative to represent clockwise rotation. So if we give these two gears a spin, the gear on the left is exhibiting positive or anti-clockwise rotation, and the gear on the right is exhibiting negative or clockwise rotation. Angular displacement is a measure of how much an object rotates. What angular change does it go through as it rotates? If you'll take a look at these two balls over here, the red and the blue ball, they will both experience the same angular displacement of pi over 3 radians or 60 degrees. Despite their different distances from the center of rotation, they experience the same angular displacement. We represent angular displacement using the Greek letter theta. You'll find that many of the quantities in rotation are represented by Greek letters. Now, you'll notice that even though they have the same angular displacement, the blue circle traveled through a greater distance. The actual distance traveled by an object that is moving along a circular path is found by multiplying its angular displacement, theta, by its radius of rotation. So even though the two circles have the same angular displacement, the blue circle traveled through a greater distance because it is a greater distance from the center of rotation. It had a greater rotational radius. If the circle made a complete path, a complete circular path, then the distance traveled would be 2 pi radians. Remember, 2 pi radians is 1 complete revolution multiplied by the radius. So you would have 2 pi r, which of course is the circumference of a complete circle. So that makes sense. Next, we need to talk about how quickly something rotates. The term for that is angular velocity, and it is represented by the Greek letter omega, which somewhat resembles a lowercase w, except with rounded bottoms. Just as linear velocity is displacement divided by time, angular velocity is angular displacement divided by time, so delta theta over delta t. And we measure linear velocity in meters per second, so angular velocity is measured in radians per second. All right, so we have a skill practice question here, and I'm going to go ahead and cut that and paste it over here to give me a little more space to answer it. It says, Earth rotates once on its axis in 24 hours. calculate Earth's angular velocity in radians per second. All right. Well, we are told that the angular velocity, we are told that the angular velocity is 1 revolution in 24 hours. And we wish to convert that into radians per second. So the first thing we're going to do is set up a conversion factor to take care of our revolutions. We want to convert revolutions to radians. So I will bring revolutions to the bottom because I want it to cancel out with the revolutions that's on the top. And I will put radians on the top because that's the desired unit. That's what I want to convert to. And from my conversion factor, we remember that 1 revolution is equal to 2 pi radians. Now the next thing we want to do is change hours into seconds. So we will set up another conversion factor. And hours is on the bottom. So over here we're going to place hours on top because again we want them to cancel out. And I will put seconds on the bottom. And 1 hour is equal to 3,600 seconds. Now we want to make sure that everything cancels out correctly. So let's see. Revolutions is going to cancel out. Hours is going to cancel out. And we're going to be left with radians on top of seconds, which is exactly what we want. So you punch the numbers into your trusty calculator, 1 over 24, multiplied by 2 pi over 1, multiplied by 1 over 3,600. And the calculator is going to tell you that the answer is 7.3 times 10 to the minus 5 radians per second. And that seems like a very small number, but remember, Earth takes 24 hours to make one complete rotation. So, yeah, the number of radians per second is expected to be a very small number. So let's move on to our next problem. Tangential velocity is just the velocity of an object moving in a circular path. If you imagine, say, a bucket tied to a rope, and the bucket's being swung around in a circular path, if the rope were to suddenly break, the tangential velocity is the velocity that the bucket would fly off in a straight line after the rope broke. The tangential velocity is equal to the radial velocity, remember in radians per second, multiplied by the radius of rotation. So the problem says the radius of Earth is 6.38 times 10 to the 6 meters. How fast is a person standing on Earth's equator moving with respect to Earth's center? So let's copy this problem and add it to our current page. And we will need to use the information that we got in the previous problem to solve this one. All right. We know that the tangential velocity, which is what we're looking for, is equal to the radius multiplied by the angular velocity. From the problem, Earth's radius is 6.38 times 10 to the 6 meters. So we will plug that in for r. 6.38 times 10 to the 6 meters. And the angular velocity, which we worked out in the previous problem, is 7.3 times 10 to the minus 5th radians per second. And so we simply multiply these two numbers together in your calculator, and the answer, when rounded to two significant figures, is 4.7 times 10 to the 2nd meters per second. Now you could also write 470 without a decimal point, but this is just more precise. So 470 or 4.7 times 10 to the 2nd meters per second. That's how quickly you're moving when you're standing on Earth's equator. And you don't feel that motion because the air and everything around you is also moving at roughly the same speed. So it doesn't feel like you're moving at 470 meters per second, but you are. The last thing we have to talk about then is angular acceleration. So linear acceleration is a measure of how quickly an object is changing its velocity. Well, angular acceleration is the same thing, except for rotation instead of linear motion. To calculate angular acceleration, which is represented by the Greek letter alpha, we simply take the change in angular velocity and divide it by time. The unit for linear acceleration is meters per second squared, or meters per second per second. And the unit for angular acceleration is radians per second squared. So every aspect of linear motion has an analog or a counterpart in rotational motion. It's normally just swapping out the meters for radians. And we have one final skill practice question here to take a look at. So let me go ahead and copy that, and I'll paste it onto a new page. What is the angular acceleration of a record that spins up to 33 RPMs, or revolutions per minute, in 2.0 seconds? All right, so we know that the angular acceleration, alpha, is equal to the change in angular velocity divided by the change in time. And the change in angular velocity, we could write that as the final angular velocity, or omega f, minus the initial angular velocity, or omega I. And of course that's divided by the change in time, which we know is going to be 2.0 seconds. So we need to figure out, what is this final angular velocity? Well, it tells us that it's 33 revolutions per minute, but I'd like to change that into radians per second. Just keep everything in SI units. All right, so omega f, the final angular velocity, is equal to 33 revolutions per minute, and we are going to convert that into radians per second. So we will go ahead and set up our conversion factor. First, I will bring revolutions to the bottom, and I will place radians on top. And remember, 1 revolution is equal to 2 pi radians. Next, I want to change minutes into seconds, so I will need a second conversion factor for that. I will place minutes on top and seconds on the bottom. 1 minute is equal to 60 seconds. And I want to make sure that everything cancels out that's supposed to cancel out. So let's see, I've got revolutions on the top and I have revolutions on the bottom, so they're going to cancel out. I have minutes on the bottom, and over here I have minutes on the top, so they're going to cancel out. And the only thing that does not cancel out are radians and seconds. So this is going to work for changing revolutions per minute into radians per second. So we punch it into our trusty calculator. 33 times 2 pi over 1 times 1 over 60. And the calculator is going to tell us that this is equal to 3.5 radians per second. Once we round it down to 2 significant figures, we get 3.5 radians per second. So that is omega f. So coming back up to our original problem, we're going to plug in 3.5 radians per second into omega f. Omega I is just the initial angular velocity, and if the record is starting from rest, or it's not rotating at all, then its initial angular velocity is 0 radians per second. And then on the bottom we have delta t, the change in time, and of course from the problem we know that's just going to be 2.0 seconds. So this is going to boil down to 3.5 minus 0, which is just 3.5 radians per second, divided by 2.0 seconds. And when we punch that into the calculator and round it down to 2 significant figures, the answer is 1.7 radians per second squared. That's going to be our final answer. So the angular acceleration of the record is 1.7 radians per second squared. So that pretty much wraps it up. I've included a table here just showing the relationship between the various linear components of motion and the angular counterparts. And you can see that Each angular counterpart is related to the linear counterpart through the radius of rotation. So the linear, or not really linear, but the distance traveled by a rotating object is equal to the radius multiplied by the angular displacement. The tangential velocity is equal to the radius times the angular velocity, and the acceleration is equal to the radius times the angular acceleration. In our next lesson, we'll start looking at some of these relationships in a little bit more detail. In the meantime, I am going to put a form on Google Classroom. I would very much appreciate it if you would go to Google Classroom and fill in that form, just indicating that you have viewed this lesson. We will also do a review on Lesson 5.2, and then we will start getting into the new material 5.3 and 5.4, which will probably be available after spring break. I appreciate your time and attention. Have a great day. Stay safe.